Hi, my name is Yahui, and my paper of selection is Flush Reload, a high-resolution, low-noise L3 cache set channel attack. And here is my outline of today's presentation. First, I will go to the background, including memory hierarchy, RSA, and set channel attack. And I will go to the paper and talk about the attack overview, how the attack works, and some examples. And then we will conclude this paper. So to start, we'll start with memory hierarchy. So what a typical memory hierarchy contains 3 levels on-chip SRAM caches, followed by DRAM main memory and a flush memory cache for the hard disk drive. Why we have these different levels? Because for registers, it's smaller, but it's also faster to access. It's normally used for address that usually specified in instructions. And for main memory, it's larger but also slower to access. It mainly used for address that usually from values in register. And if a location is referenced, the memory reference takes advantage of locality. It takes temporal locality as the current reference location is likely to be referenced again in the near future. It also takes spatial locality as the location near it will be referenced in the near future. The memory references follows the locality principles where it keeps the most often used data in SRAM and only refer to main memory for the remaining data. And here's a table of different components, their access time, capacity, and who manage them in the operating systems. And cache. Cache is SRAM component, and the main purpose for it is to provide low latency access to recently accessed memory systems. For here, we have processors, we have cache, and we have main memory. If the processor wants to send an address to cache, then if the data is found in the cache, it will return the copy of data from the cache directly, which is called a cache hit, and this usually takes less time. If the data is not found in the cache, then you will go to the main memory to fetch the data and send it back to the processor. It will also retain the data into the cache. This process will be slower as it will go to the main memory, and for replacing data in the cache, if the cache is full, it will also replace some other data if needed, and it will follow other replacement policies which will be covered here. And we come to memory sharing. In many scenarios, we share memories when we reuse code to reduce overall memory footprint of the system. We can share the text segments, we can share libraries, or we duplicate the memory. In the shared memory architecture, the entire memory, for example, the main memory and the disks, are shared by all processors. Special and fast interconnection networks allow any processor to access any part of the memory in parallel. All processors are under the control of a single operating system, which makes it easy to deal with load balancing. It is also very efficient since the processor can communicate via the main memory. Some strength of this shared memory architecture, first of all, is the simplicity, as the intra-processor are similar to single processor computers. Also, we can reuse code as sharing the code copies across multiple instances. We also have the load balancing, which will be achieved at the runtime by allocating each new task to the least busy processor. And then we come to RSA. RSA is the most popular public key cryptography system, and this public key algorithm requires to calculate a pair of key of public and private. The idea of RSA is based on the fact that it's difficult to factorize a large integer. The public key consists of two members, where one member is a multiplication of two large prime members, here, P and Q. Uh, and the private key is also derivative from the same two primary numbers. So if somebody can factorize the large number, the private key is compromised. Therefore, the encryption strength totally relies on the key size. And if we double or triple the key size, the strength will increase exponentially. So far, we have 1024 bits RSA keys, which has not been broken yet. A simplified process of how RSA works. If Alice wants to send an encrypted message to Bob, she will first encrypt the message using the encryption exponent E and Bob's public key. And when Bob receives the message, he will decrypt using the decryption exponent. A square and multiply algorithm is an extension of RSA. What it does, it is trying to scan the bit of exponent from the most significant bit to the least significant bit, which is left to right. And in each iteration for every exponent bit, the current result is squared if and only if the current scan exponent bit has value of 1. A multiplication of the current result by x is executed following the squaring. The purpose of this is that the sequence of the operations reveal the secret exponent. For example, if we have square reduce, that means clear bits. And if we have square reduce, multiply reduce, that means we're trying to set a bit. And this is what GNUPG uses, which is a attack example in the paper. And we come to set channel attack. The set channel attack means the attacker trying to extract implicit information that unintentionally leaked out through radio signals, execution time, power consumptions, or through the states of computer processors' memory cache. The purpose of set channel attack mainly have two categories. First is trying to extract secret keys from cryptography implementations. Back in 1999, this paper extracted the secret RSA key from a smart card only by looking at the amount of power it uses. And in 2013, another paper extracted a secret RSA key by just listening to the sounds a computer makes while decrypting data. And the second category is the attacker trying to compromise user privacy. For example, from the keystrokes, it can recover the accelerometer data on smartphones. Or from a web application, it can determine which medical conditions the user was searching for, what their income range was, and how they allocated the investment funds from the user input. Here comes to the paper. So the overview of flash and load, which is the topic talking from the paper, it's a L3 or last level if the system doesn't support L3 cache. Set channel attack that take advantage of executable code page sharing between process. The spy process first capture victim secret through the interfering with the victim cache access patterns, and it will also leverage the latency difference of the cache access to memory lines in different status to infer the victim behavior. Mainly, there are two types of set channel attack. One is flush-based, meaning flushing the memory lines using cflush instruction, which is this paper used. And also, there's another type called eviction-based, which replacing memory lines with spiced memory lines. very brief walkthrough of flash load attack here. So if Alice is the first one to run the program, the operating system will load the program into physical memory. When Bob runs the same program, instead of loading a second copy into the memory, the operating system will set Bob's page table to use the copy that was loaded into the memory for Alice. The result is that both Alice and Bob are using the same physical memory. This is safe because the code is stored in read-only memory, so neither of the users should affect each other. However, if Bob can determine which cache lines of the shared memory are present in the cache over time, he can tell which cache line Alice process accesses over time. Here's a more detailed timeline of how this attack works. Suppose that an attacker knows the victim's running program and wants to see which code the victim process is running. The attacker first selects a few cache lines to watch and then flush them out of the cache, wait for a certain number of clock cycles, and time how long it takes for them to reload the lines. If the reload is fast, that means the victim has accessed the line during the waiting time period. If the reload is slow, that means the victim didn't access the lines, so the lines need to be brought from memory. And the attacker can repeat the process until allocate the cache lines that the victim is actually using. Figure A here shows that if the victim didn't access it, it will take longer for the attacker to reload it. Figure B shows, on the contrast, with victim accessing the cache, it will be brought to the cache, and the loading time for attacker will be shorter. And it's very possible for victims' access and attackers' reloading overlap each other. If victim access while the spy is reloading the lines, then the victim access will not trigger the cache field and will use the cache data from the reload phase. Consequently, the spy will miss the access. If the reload process starts while victim is waiting for the data, the reload will benefit from the victim access and will be determined faster than the data as has to be loaded from memory. However, the timing might be still longer than the load from the cache. To reduce the missing probability of overlapping, one way to improve the resolution of the attack without increasing the error rate is to target memory accesses that occur frequently, such as a loop body. The attack will not be able to discern between separate accesses. For example, the figure E shows. The likelihood of missing the loop is small. So this paper attacked GNUPG using the flash and load technique. So it first achieves the sharing of victim code. It uses flash and load to recover the sequence of operations of the modular exponentiation. It then divides time into slots of 2048 cycles, and in each cycle, it probes a memory line in the code of square, multiply, model, reduce functions. The approach is to trace the execution time of the victim process. In this below figure, it shows the measurement times of 100 time slots of the GNUPG signing with a 2048-bit key. In each time slot, the spy flushes and then measures the time to read the memory lines in the square, multiply, reduce functions. Measurement under the threshold indicate that the victim access to respective memory lines. And here is a zoom in of the time slot. We can see it's a sequence of square, reduce, multiply, and reduce. That indicates that during these time slots, the victim was processing a set bit. here are more real-world examples that being studied after this paper. So we assume we have a shared system, and the attack applies flush and load in non-cryptography settings to meaningfully violate the confidentiality. This paper did 3 different experiments. First one is for the detector to determine which of the top 100 Wikipedia pages a user visited in the link's web browser. Second one is to determine which of the 127 PDF files a user passed to PDF top commands. And the last one is to determine whether the true crypt volume a user just volume was a hidden volume or not. These experiments was tested on 2 different Intel processors. The first one is Core 2 Dual P8700, which was launched on Q4 2008, and another one is Exxon E31245, which was launched later in Q2 2012. The system 1 doesn't have all 3, but the flush and reload also works on it with its L2 caches, as it is shared between cores. So we come to the conclusion of this flush and load paper. The first strength it is this technique is very resistant to noise, as we are flushing and drilled into one memory block. That means if some noisy process in the system want to create noise, they must fill the entire set to create an access. The second advantage is it is applicable across CPU socket, because the flush instruction does not only flush from the last cache, but also invalidates the memory block and will provoke that other CPU sockets also invalidate them and block them from their caches. Since we have some fast links between CPU to retrieve data faster from another CPU circuit cache, this attack is fully applicable in cross CPU circuits, and also for the same reason do not acquire inclusiveness property, because the validation will also invalidate the block even in non-inclusive environment. The weakness of this attack: first of all, it has limitations on the system. For example, some cloud providers implement the copy and write as a countermeasure, and most of the mobile devices, the C-flush instruction is not available. And also, it really depends on the memory location. We can only recover statistically allocated data and code, so dynamically allocated data that go through the heap cannot be accessed. And that's my presentation. Thank you.